Imagine a universe filled with invisible forces, where unseen and mysterious entities quietly manipulate the very fabric of reality. Among these enigmatic objects are primordial black holes, ancient remnants from the earliest moments of the universe. Formed shortly after the Big Bang, these black holes may have played, and may still be playing, a critical role in shaping the cosmos as we know it. But what are these primordial black holes? And how do they differ from the more familiar black holes we know today? To answer this question, we need to take a journey back in time to the beginning of the universe, just moments after the Big Bang. The universe was in a state of extreme chaos, an incredibly hot, dense mixture of particles and energy. As the universe expanded and cooled, tiny fluctuations in the density of matter began to occur. In regions where the density was particularly high, gravity could have caused the matter to collapse in on itself, forming what we now call primordial black holes, PB8ers. These black holes are unique because they didn't form from the death of massive stars, as most black holes do. Instead, they were born out of the fundamental processes that governed the early universe. Primordial black holes could vary dramatically in size, from subatomic scales to masses larger than our sun. Some theories even suggest that the smallest primordial black holes could have evaporated over time due to a process known as Hawking radiation. However, those that are more massive could still be lurking in the universe today, invisible to our telescopes, yet influencing the cosmic environment in profound ways. But why are primordial black holes so important? One of the most compelling reasons is their potential connection to dark matter, a mysterious substance that makes up about 85% of the matter in the universe. Despite its abundance, dark matter has never been directly observed. Its presence is inferred from the gravitational effects it has on visible matter, like galaxies and stars. One hypothesis is that primordial black holes could account for at least a portion of dark matter, particularly in the planetary mass range. This idea is still a topic of intense debate within the scientific community, but if true, it could provide a critical piece of the puzzle in our understanding of the universe's composition. In recent years, astrophysicists have been exploring the possible interactions between primordial black holes and stellar systems. For instance, a binary star system, a system where two stars orbit each other, could be significantly disrupted by the gravitational influence of a passing primordial black hole. This disruption could have a variety of outcomes, depending on the specific conditions of the interaction. One particularly dramatic scenario is the ejection of one of the stars from the system. Imagine a star being flung out into the depths of space, while the black hole takes its place in the binary system. Such an event would not only be catastrophic for the star, but could also provide a unique signature that we might be able to detect. But what makes this idea even more intriguing is the possibility that these interactions are not just theoretical. Observational evidence suggests that there could be binary systems within our own Milky Way galaxy where one of the components is a primordial black hole. Detecting these systems would not only confirm the existence of primordial black holes, but also provide crucial insights into their properties and behavior. The study of primordial black holes is also closely linked to the field of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as black holes. In 2015, the LIGO Observatory made history by detecting gravitational waves for the first time, a discovery that opened up a new way of observing the universe. Since then, there has been growing interest in the idea that primordial black holes could be responsible for some of the gravitational wave signals we've detected. If two primordial black holes were to merge, they would create a powerful burst of gravitational waves that could be observed by detectors like LIGO and Virgo. Such a detection would not only provide direct evidence of primordial black holes, but also offer new insights into the nature of black holes and their role in the universe. Another area of research involves the potential role of primordial black holes in the formation of galaxies. Some scientists speculate that primordial black holes could have acted as seeds for the formation of supermassive black holes, which are found at the centers of most galaxies. These supermassive black holes have masses millions or even billions of times that of the Sun, and their origins remain one of the biggest mysteries in astrophysics. If primordial black holes did indeed play a role in their formation, it would suggest that these ancient objects had a profound impact on the structure of the universe. In addition to their potential role in galaxy formation, Primordial black holes could also be responsible for some of the most energetic phenomena in the universe. For example, gamma-ray bursts, intense flashes of gamma rays that occur when massive stars collapse or when neutron stars merge, could be linked to the interactions of primordial black holes. Similarly, fast radio bursts, FRBs, which are brief but powerful emissions of radio waves from distant galaxies, might also be connected to these mysterious objects. While these ideas are still speculative, they highlight the potential importance of primordial black holes in understanding some of the most extreme events in the cosmos. Detecting primordial black holes, however, is no easy task. Because they don't emit light, they are virtually invisible to traditional telescopes. Instead, scientists must rely on indirect methods to infer their presence. One approach is to look for the gravitational lensing effect that occurs when a black hole passes in front of a distant star. The black hole's gravity bends the light from the star, causing it to temporarily brighten. By monitoring large numbers of stars, astronomers can search for these telltale signs of a passing primordial black hole. Another potential method involves studying the cosmic microwave background, CMB, the afterglow of the Big Bang. Primordial black holes could have left imprints on the CMB through their gravitational effects, and by carefully analyzing the CMB, scientists might be able to detect these imprints. This would not only provide evidence for the existence of primordial black holes, but also offer new insights into the conditions of the early universe. The search for primordial black holes is not just about solving a cosmic mystery, it's about expanding our understanding of the fundamental laws of physics. For instance, the study of these objects could shed light on the nature of quantum gravity, a theory that seeks to unify general relativity, which describes gravity on large scales, with quantum mechanics, which governs the behavior of particles on the smallest scales. Understanding how black holes, including primordial ones, interact with the quantum world could lead to breakthroughs in our understanding of the universe at its most fundamental level. Moreover, primordial black holes could provide clues about the nature of time itself. Black holes are known to warp space-time, and studying how primordial black holes have evolved over billions of years could help us understand the nature of time and its relationship with gravity. This could have profound implications for our understanding of the universe and could even inform the search for a theory of everything, a single, unified theory that explains all the forces of nature. As our technological capabilities continue to advance, so too does our ability to study these elusive objects. Future space missions, such as the Laser Interferometer Space Antenna, LISA, will be able to detect gravitational waves with even greater sensitivity, potentially allowing us to observe the mergers of primordial black holes in distant galaxies. Additionally, new telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope will provide unprecedented views of the universe, potentially revealing the signatures of primordial black holes in the light of distant stars and galaxies. But what if we could go even further? Some scientists have proposed that we could one day create miniature black holes in particle accelerators, like the Large Hadron Collider. While these black holes would be tiny and short-lived, they could provide valuable insights into the behavior of primordial black holes and the conditions of the early universe. This idea, while speculative, represents the cutting edge of research in this field and highlights the potential for future discoveries. In conclusion, the study of primordial black holes is a rapidly evolving field that touches on some of the most fundamental questions in physics and cosmology. From their potential role in dark matter to their influence on the formation of galaxies, these ancient objects could hold the key to understanding the universe in ways we can only begin to imagine. As we continue to push the boundaries of science and technology, the mysteries of primordial black holes may one day be unraveled, offering us a deeper understanding of the cosmos and our place within it. So, what do you think? Could primordial black holes be the missing link in our understanding of dark matter? Could they be the key to unlocking the secrets of the early universe? And what other surprises might they hold? Share your thoughts in the comments below. And don't forget to like, subscribe, and hit that notification bell for more deep dives into the mysteries of space.